Okay. So hi Rasika. So let's wait for 5 minutes so that a few more people can join the meeting. So I guess I'll start in 5 minutes. Just waiting if some others also want to join the meeting. So I'll start. So yeah. Okay, so I guess we can get started since no others are joining. So yeah, so hello everyone. Just to reintroduce myself, so I'm Lakshay Saggi, the NPTEL Competitive Programming course TA for the Tuesday problem solving sessions from 6 to 8 p.m. So this will be, I believe, our 10th session. And in this session, we'll be covering like the topics discussed in this week's lectures, which were mostly related to dynamic programming. So yeah, today we'll be covering problems related to dynamic programming and the problems which were covered in the lectures. So like I hope my voice is clear to everyone, and so I guess we can get started with the problems. So I'll just share my screen. So let me just share my screen, guys. Okay, so Harsha is raising his hand. So is there some doubt, Harsha? Uh, is my audio not clear, Harsha? Okay, hello. So yeah, so actually, if you have any doubts or anything, then you can type in chat. So yeah, I have muted the audience because it can cause some disruption in the class. So if there are any doubts in the session, or if you want to say anything or any comments, you can type in chat. So yeah, I'll be seeing the chat as we go along. Okay, so the answers for programming assignments for previous weeks. So I don't know much about the programming assignments because I'm just the problem solving TA for the course, Asha. So I don't know much about programming assignments, but I believe you can ask this question in the discussion forum for the course, and I guess the relevant people can answer there. So like I just know about these problem solving sessions which I take on these Tuesdays and their answers. Oh, you have already asked and there has been no answer from past weeks. Okay, that's strange. Uh, but yeah, I don't know. Maybe I believe there's also a Discord server for the course, right? So you can ask there also. Yeah, definitely. It would help if you get the answers for the same. But like I don't know, like okay, you already also asked in the Discord server, but no answer in that either. Oh my god. So yeah, like, but I'm definitely not the relevant person for this question. So sorry for this, but yeah. So maybe we can proceed with the problems, I guess. So I'll just share my screen so that we can get started with the problems. Okay, okay. So Harsha is asking, can DP answer be also used to solve like min cost max flow and vice versa? So what do you mean by DP answer first of all, Harsha? So uh, like min cost max, let's not talk about min cost max flow. It's a more general version of max flow, uh, but even like using DP, I don't think there is no algorithm which uses DP to solve max flow. So yeah, like I understand DP is dynamic programming pattern, but what I'm saying is you have to be specific in the what algorithm are you using, right? But as far as I know, like there is no algorithm which uses techniques of dynamic programming to solve max flow. So most of the existing algorithms for max flow use this idea of residual graphs and something only. Okay, so like that's what I'm saying, Asha. like I don't know of any algorithms which use DP to solve problems like min, cost, max, flow. So I believe there are none because mm, memorization generally does not help in these kind of problems, and you need concepts of residual graphs and stuff. So yeah, like I believe that like at least there is no trivial or like well-known algorithm which uses GP to solve these problems. So yeah. Okay, so yeah, so Harsha is asking finite state machines as DP for min, cost, max, flow. So again, Harsha, I don't think there are any algorithms in the literature which uses finite state machines for DP for min, cost, max, flow. Like you can search on it further also, but I'm pretty sure that like most of the algorithms use concepts of residual graphs and stuff only, and don't use these kinds of memorization techniques to solve these max flow problems. Because like you can think of it also like what sort of DP can we make to find max flow? Because a flow from a source to a sink may not be uh, trivial to solve using memoirs. So yeah, I understand that you can have a state number for each node, but like then you sort of need. So you're saying that we can have a state number for each node, but what I'm saying is uh like for a vertex, I don't know why the max flow for on that vertex should be dependent on the max can be calculated using the max flow on the previous vertices and something like that. So this sort of relation is, I don't think, trivial or like at least known in the literature or something. So yeah. So maybe you can search on it by yourself offline also, but I believe that you will not find much about this. But if you think like there can be some argument or something which can be used to solve max flow using DP, then you're welcome to mention that argument or like. So yeah, like if you like you can work it if you are able to work it out yourself, then I'll be happy to take it like in the next session, or you can maybe join the next session and tell me about your ideas and stuff. So yeah. So for now, I believe we can move on to the we can move on to problems of this session. So yeah. So I was just sharing my screen. So uh, okay. So I hope my screen is visible to everyone. So yeah, so this is a 10 session, and like I have created some 8 problems. So for you guys to be able to solve the assignments which you guys get for weekly assignments. So yeah, so maybe we can uh, move on to the first question. Like first 2 questions are like just theory based questions, like very trivial questions. So yeah. So the first question says that which of the following best describes dynamic programming? So which of the following options best describes dynamic programming? So we often say that breaking down a complex problem into smaller, more manageable subproblems, solving those independently, and then combining their solutions to obtain the solution. A method for solving or breaking them into smaller subproblems and storing the results to avoid redundant computation. C is a programming paradigm that involves making a series of choices, and D is a programming paradigm that uses dynamic data structures. So, so yeah. So Harshai is saying in the chat that the answer for this should be B. So yeah, so this is a straightforward question. Like in dynamic programming, what do? We break the problem into smaller sub-problems, and for each of those sub-problems, we store the results so that we don't have to compute the results again. So we use some more memory to avoid computation at the so we use more, so we avoid computation at the expense of some more memory, and this results in avoiding redundant computation. So yeah. So just going through the options. So A option, breaking down a complex problem into smaller manageable problems and solving those independently. This is what we call recursion. Like A option is just describing the recursion technique. And if we store the results also, then recursion using memory is called dynamic programming, which is the B option describes. And what does C option describe? What does C option describe, guys? So you have also gone through this paradigm, like a paradigm that involves making a series of choices where decision is made by selecting best available option till now. So what do we call this sort of technique, if you guys remember? So yeah, so Harish and Rasika both are saying greedy. So yeah, good job, guys. So yeah, this is what we call the greedy. Like this is the greedy approach. And the option, like you can leave a programming paradigm that emphasize using. We don't need to get into that. So for this, the correct answer is option B. And just this is just the definition of DP paradigm or something like that. Like not exactly definition or just description. So just for mentioning, option A describes recursion and option C describes greed. So yeah, something like that. Okay, then I guess second problem is also just a theory-based problem. I promise these are the only two problems which use these which are of this type. So second problem says that which of the following statement is true about memoization in dynamic programming. So memoization is what we call the using memory to store the results. So which of the following is true about memoization? So it is a way to store the solutions to reuse. It is a way to divide a problem into smaller subproblems. It is a way to make locally optimal choices. It is a way to backtrack from a wrong decision. So this is quite easy. So yeah, so Rasika is saying that the correct answer should be A. So yeah, correct, Rasika. Like memorization, it's in the name itself that we use memory. So actually, it's just a way to store the solution of subproblems to reuse. So yeah, answer is an A. So this is just the again, this is just the description of memorization. So yeah. Okay, maybe I should zoom in a bit so that the font is a bit clear to everyone. So, so let's move on to the third question then. So once again, just mentioning that I'll be assuming while discussing these problems that you guys have gone through this week's lectures because this problem frog. So like I'll be assuming that you guys know what dynamic programming is and you know a bit on how to apply it. So yeah. So this was the problem which was discussed in the lecture, also in this week's lectures. Consider the problem frog when discussing the lectures. What would be the minimum possible total cost for a sequence of height of stones? So you may not remember the frog one problem exactly. So I have this problem written here also. So I'll just uh, is the problem here. Right? This is the frog one problem. Okay, maybe I should move everything to the next page. So yeah. So this was the problem statement, the frog one problem. So we are given suppose n stones which are numbered from 1 to n, and for each of the stones for each of the n stones we are given the height of the stone also. So height of stone I is hi, and there is a frog who is initially on stone 1. So initially the frog is at this stone which is of height 10, and now he will repeat the following action some number of times to reach stone n. So what actions can the frog actually repeat? So if the frog is currently on stone I, then frog can either jump to stone I plus 1 or stone I plus 2. So initially frog is at stone 10, then it can go to 27 or it can go to 11. Similarly, after going to let's say 11, it can go to 25 or 26. So it can go to the next stone or just the stone after the next stone. So, and whenever the frog jumps, a cost of the absolute difference of the heights is incurred. So let's say if the frog jumps from this 10 to 27, then frog has to pay a cost of 17. 27 minus 10 is 17. Similarly, if the frog goes from let's say 27 to 11, the frog has to incur a cost of 27 minus 11, which is something like a 16. So find the minimum possible total cost incurred before the frog reaches the stone end. So frog has to start from this stone 10 and the frog has to reach this stone 38. And now we have to find a route for the frog to minimize the total cost incurred. So, so what we actually want to do is the path taken by the frog should be such that the sum of cost incurred at every step should be minimized. So this problem has been discussed in the lectures also, but still I believe we can formulate it by ourselves also. So what can we do is let's say we assume that Tn is the uh, minimum cost to reach the nth stone. So let's say for any n, let's say we denote by Tn the minimum cost required to reach the nth stone. So here, like in this problem, suppose we want to find out the minimum cost for to reach the 27, the stone 27. For this n would be 2, for this stone n would be 3, for this n would be 4, and so on. So now we can formulate a relation for like how to compute Tn. So what does dynamic programming do? It solves some previous sub problems, and from that it solves the current problem. So here also we can sort of do that. Like we can solve the problem for Tn if we know about some previous stones also, about some previous sub problems also. And why is that? So if a frog has to reach the nth stone, then we know that a frog can only jump from stone I to stone I plus 1 or I plus 2. Right? So what this means is that if a frog has to reach the nth stone, then this last jump would have been from either n minus 1 to nth stone or n minus 2 to nth stone. I hope you guys understand what I'm trying to say. So if frog has to reach the nth stone, the frog can reach this stone from if the frog jumps from n minus 1 stone to the nth stone, or if the frog jumps directly from n minus 2th stone to the nth stone, because these are the only two jumps possible for the frog. Like the last jump can be a jump of size 1 or a jump of size 2. So yeah. And what do we actually want? So what we want is actually the minimum of these two costs. And like what do we actually want the minimum of? Are these two steps. So frog reaches till n minus 2th stone and then jumps to nth. So this is one possible way. And the second possible way is that frog reaches till n minus 1th stone and then jumps directly to nth. So I hope you guys understand like the sub problem, like why will this thing be true? So what we want is so these are the two possible ways in which frog can reach the nth stone. And since we want the minimum possible cost, so we take the minimum of these two ways. And how can we quantify these costs? So what this implies is that Tn is nothing but a min of. So what would be the cost for this? Like how can we write down the cost for this step? Like if frog is reaching till n minus 2th stone and then directly jumping to nth stone. So we can write it like this. So first the frog reaches till n minus 2th stone. So remember how did we define Tn? We defined Tn as the minimum cost to reach the nth stone. Similarly, frog for minimizing the cost of reaching n minus 2th stone, we can write something like a T of n minus 2. And then, so first frog reaches till n minus 2th stone and it will try to minimize the cost taken till here and then directly jump to nth stone. So the cost of jumps till this part and then the cost of the jump in this part. So the cost of the jump in this part will be nothing but the absolute difference in heights of these two stones. So hn minus h of n minus 2. So something like this. So I hope you guys are able to follow that. Why will this sort of term be true? And similarly, what will the second part? Here we'll just replace n minus 2 by n minus 1 because frog reaches till n minus 1 stone and then jumps directly to n stone. It will be the absolute difference in the heights or something like this. So yeah. Okay. So like this all has been discussed in the lectures, but I'm just doing this again because like essentially these sorts of things are how you do dynamic programming, right? So yeah. So to reach the end stone, there are these two possible ways. And so we have sort of obtained a relation like how can we compute Tn if we have already solved Tn and Tn minus 1 and Tn minus 2, then we can easily solve T of n also using this sort of relation. So we can just use this relation to find out the answer for this part also. So how can we do this? So maybe we can just copy and paste the sequence here. So what are the heights of stones? Heights are something like this. So heights are something like this. Heights of stones are given at this 10, 27, 11, 25, and something like this. So also like the minimum cost to reach the next stone if the frog is starting from first stone itself. So frog is always starting here and then we need to find out the minimum cost. That's when this sort of relation will hold. So once again, guys, if you are not able to follow, if you don't understand something at any point of time, please feel free to write it in chat and I'll try to explain that again. So if you don't write anything, I'll just assume that everything is going smoothly. So yeah, so do ask questions if you have any. So we know that T of 1 will be, so we don't need this sort of relation to find out T of 1. T of 1 will be just the minimum cost required to reach the first stone if the frog is starting from first stone itself. So this will be 0 because uh, frog is starting from the first stone, so we don't need to compute this. Similarly, for T of 2, so T of 2 means that frog is starting from first stone and it has to reach the second stone. So there is only one way in which frog can reach it, which is of jumping from 10 to 27 directly. A frog can't make the 2 length jump here. So here the cost will be 17. Like it will be something like maybe I should write it better. 27 minus 10, it is 70. So yeah. So these are the base cases of the problem which we can directly compute. Right? T of 1 is 0 and T of 2 is 70. Now to find out T of. So now what we need to find out is something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 stones. So we need to find something like a T of 12. But for these, we will need something like T of 11, T of 10, T of 9, and so on. So we'll be computing these progressively. So we'll compute T of 1, T of 2, and then T of 3 can be computed using these two values. Then T of 4 can also be computed in the similar manner and so on. So we'll just be computing these step by step. So T of 3 will be nothing but so now for T of 3, we can use this sort of relation because in T of 3, the terms inside coming will be something like T of 1 and T of 2, which we have already computed. So T of 3 will be something like a minimum of T of 1 plus the height from the difference in heights of 3 and 1. So 11 minus 10 will be something like a 1. And the second option will be T of 2 plus maybe I should write it a bit clearly here and we can we can do it directly for other parts. And the second part will be T of 2 plus difference in heights of second and third. So these two. So it will be 27 minus 11. Like 11 minus 27. And this will be nothing but a minimum of so T of 1 is nothing but a 0. So 0 plus 1, comma, T of 2 is 17, and this will be 16. So 17 plus 16. So this is nothing but a minimum of 0, minimum of 1, comma 33. And this will be uh, just a 1. So yeah. So we get that T of 3 is 1. Now we'll compute T of 4. So T of 4 will be nothing but again using this relation, it will be minimum of T of 2 plus difference in heights of 4 and 2 and T of 3 plus difference of heights of 4 and 3. So something like this. So T of 3 is nothing but a 1 and okay, maybe we should do it. So T of 2 is so T of 2 is nothing but a 17. And then the difference in heights of 4 and 2 is just a 2. Like 27 and 25 have a difference of height of 2. I'm doing this directly now. And the second case can be going from the third stone, directly to the fourth stone. That will be something like a 1 plus so 1 plus the difference in height of these two stones, which will be 14. So this will be 1 plus 14. So here the answer will come out to be 15. This is 15, this is 19. So yeah. Okay, so similarly, T of 5 will be again, so T of 5 will be again, we need to go to this stone. So we can go from 4 or we can go from 5. So going from 4 will take 15 plus 15, which is 30. So I'll be doing it a bit faster now since we are just repeating the problem now and we are doing nothing new. So T of 5 will be so T of 5 will be nothing but 15 plus a 1. Sorry, because we are going from T of 3. So it will be something like a 16. And similarly, it can go from this stone to this stone directly, which will be something like a 15 plus 1, which will again be 16. Oh, wow. So this will again be a 16. So I hope everyone understands the steps and like we can follow these steps to obtain T of 12 in the end. So I don't remember the exact answer right now, but while uploading this document, I'll upload the exact answer for this problem also. So I hope you guys have understood like how to do this. Yeah. So initially we had the base cases and then we compute remaining TI using the recursive relations. T of 3, 4, 5, 6, and we can also compute T of 12. Okay, so this was the problem. This was a problem discussed in the lectures also. This is not a problem statement, but yeah, we have just discussed this again. And now we have the fourth question. Okay, so Harsha, you are asking where do I upload the document? So maybe I'll in this chat only I'll share the link of the drive where I upload. So uh, I don't have the link right now, or maybe I have. Let me just see. So there will be. Okay. So there are bookmarks. Okay. So I'll just. So I have posted in chat the uh, drive link where I upload these documents. Uh, so yeah, actually, Harsha, there are also recordings of these lectures also. So you can access the recordings, I believe, from the NPTEL course. Like the I upload all these lectures on YouTube, and I believe at your NPTEL portal, there's you guys will be able to obtain the link to the videos. So if you don't, maybe I can just tell you guys about one of the. I can just send in chat one of the links also. So 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 like this is the link for the previous week's lecture, and actually I created a playlist. So in that playlist, yeah. So you can. So I've shared the link of the previous week's lectures video, and you can see the playlist from this link only. Asha. So you can go to this video and you can see that it's part of a playlist, and from this playlist, you can obtain. So, okay, so I hope you are able to see the links in the chat. Okay, sure. So you're, yeah. So maybe we can then move on to the next problem. So the fourth question says, consider the problem dice with combination discussed in the lecture. So again, this is a problem which has been discussed in the lecture. So uh, I'll just give the problem statement here also, so that you guys, like you may not remember the problem statement, so it would be easier if I just share it with you guys again. So the problem is very simple. The problem just asks that uh, so, yeah. So the problem says that yeah. So problem says that your task is to count the number of ways to construct a sum of n by throwing a dice one or more times, and each throw produces an outcome between 1 and 6. So what we are asked to compute is, suppose we can throw a dice any number of times, and each throw produces an outcome between 1 and 6. So we just need to find out the number of ways in which we can construct a sum of n. So there is no restriction on the number of throws which we can make. But note that just from this problem, like suppose if we have to construct a sum of n and each throw produces an outcome between 1 and 6, then we don't need to do more than n throws of the dice anyways. Because in every throw, a number of at least 1 will be produced. So after n throws, at least we know that sum will definitely be uh, greater than equal to n. So sum will be at least n. So yeah, so just mentioning that even though we have one or more times throws, like the throws will be restricted by n. It doesn't matter in the question that much, but yeah. So okay, okay. So this also has been discussed in the lectures, but maybe we can do it here also. So again, in this problem, like previous problem, we'll use something like a recursion or dynamic programming based technique. So in previous problem also we defined something like a T of n, right? So here also we can define something like a T of n, and T of n will be nothing but the number of ways to construct a sum of n. Then I claim that I can write a recursive relation for this T of n using the previous values, the T of n minus 1, T of n minus 2, and so on. So would one of you like to, like Rasika or Rasha, would any of you like to mention in the chat what sort of recursive relation will there be for T of n? Like how can I compute T of n from previous values? Okay, so Harsha has already mentioned in the chat that use the constraint sum minus 1 to 6. So yeah, I guess I get the idea of what Harsha means to say. So what we are actually doing is, so suppose there's a sequence of dice throws, right? So we know that the last throw, like suppose we there's a sequence of dice throws from which we obtain a sum of n. So the last time which we throw a dice, the last time the number which comes up can be any number from 1 to 6, like 1, 2, 3, 4, 5, 6. So what it means is that if 6 comes up, this means that we could have created the number still n minus 6 in any ways. And in the last row, we would have just created the number. We would have just thrown the number 6. So it will be like the number of ways to throw, the number of ways to obtain a sum of n such that the last row shows up 6 will be something like a T of n minus 6. So I'm not writing all of this. I'm just doing this orally. So T of n minus 6 just represents the number of ways in which we obtained a sum of n minus 6 and then the last row ended in a 6. Similarly, T of n minus 5 will denote the number of ways in which the last row ended with a 5. Similarly, T of n minus 4, which denotes last row ending in a 4. Similarly, T of n minus 3 plus T of n minus 2. And the last row can also end with a 1, so T of n minus 1. So this will be the recursive relation which we get. So again, we see that T of n can be computed if we already know these previous values, n minus 1, n minus 2, n minus 3. And now we want to find out T of 12. So it can be found by again just finding out these sorts of values. Okay, so finding out these values can also be easy. So first of all, we need to find out all the base cases. So what will be the base cases? So base case will be something like so the number 1 can only be made in one way, which is just throw a 1, and anything less than 1 cannot be made. So T of I. So maybe I should write like this. So T of I is 0 for all I less than 1. So if I is less than 1, like if T of 0, T of minus 1, T of minus 2, everything will be zero because we cannot make a sum of zero or a negative sum using Dye's rule. And similarly, T of 1 will be uh, just equal to 1 or something like this. Okay, I believe T of 0 is also a 1, sorry, guys. And so these are the base cases. So T of I will be 0 for all I less than 0. So we can't have a negative throw, but there is one way to make a sum of 0. And what is that way? If someone would like to mention in chat. So yeah, Harsha, we can also use sigma n minus I as I goes from 1 to 6. Uh, that's also correct because, but like since these are not a lot of terms, I just wrote all of these together. But you can use summation also. In fact, like I would recommend that it's a more cleaner notation. So right now I'm asking like, do you guys agree with this statement that T of 0 will be 1? Like there will be only one way, there will be one way to make a sum of 0. Do you think this is correct or this is incorrect? Yeah. So Rasika is saying that if we do not get any values from 1 to 6 on the dice, then we get the sum 0. And Harsha is saying that 0 can't be made. So, uh, so actually, Rasika's argument is on the right track. So like T of 0 is actually equal to 1 because a sum of 0 can be made because suppose if you don't throw any die, then T of 0 can be made. Yeah, the question asks us that we need to throw a die one or more times, but like we can relax this also. We can relax this constraint also. Like let's say by throwing a die 0 or more times, if we just relax the question, it doesn't change the answer for us anyways. So in that sense, we can say that T of 0 will be equal to 1 and T of 1 will be 1 because 1 can be made in only one way. And one reason why I'm sort of assigning T of 0 as 1, you can also see it as just so that I can respect this recursive relation. Like for finding out T of 1, what I need to do is T of 1 will be equal to T of minus 5 plus T of minus 4 plus T of minus 3 plus T of minus 2 plus T of minus 1. So all of these will be 0. We definitely know. And then we'll get plus T of 0. And this T of 0 will then also be equal to 1 because T of 1 we know is 1. Because there's only one way to make 1. So we'll also get something like T of 0 is also 1. Yeah, so Harsha, so yeah, the question, so yeah, definitely that's good thinking on your part, Harsha, actually, that since we are asking the question that we can throw a die one or more times. So we can't make a sum of 0. But let's just relax the problem a bit. This makes our life a bit easier. That's why I'm relaxing this. So like we just assume that die can be thrown 0 times also. Then we can make T of 0 as 1 also. So now how do we compute T of 2? So T of 2 will be nothing but T of 1 plus T of 0. And then all the negative values don't matter to us. So T of 0 plus T of 1 will be nothing but 2. So maybe I should put this as 2. Then T of 3 will be nothing but T of 2 plus T of 1 plus T of 0. So T of 2 plus T of 1 plus T of 0, which will be 4. 2 plus 1, which is 4. Similarly, T of 4 will be 4 plus 2 plus 1 plus 1. So I hope everyone is able to understand what I'm doing here. So this will be something like 8. Similarly, T of 5 will be again T of 4 plus T of 3, 8 plus 4, 12. So 8 plus 4, 12, 12 plus 2, 14. 14 plus 1, 15, 15 plus 1, 16. And then T of 6 will be sum of all these values, so it will be something like a 32. And then T of 7 will just be sum of the last 6 terms, so it will be like T of 1, T of 1 plus T of 2 plus T of 3 plus T of 4 plus T of 5 plus T of 6. So it won't include this number, so it will include some from this. So 1 plus 2 plus 4 plus 8 plus 16 plus 32. So this will come out to be 63 actually. And then T of 8 will come out to be 2 plus 4 plus 8 plus 16 plus 32 plus 63. The last 6 values will be this. So it will come out to be something like so it will be 6, 6, 14, 30, 62, and then this will be 125. So we can compute this. You can compute this yourself also, but like I've gone this far, so I may as well solve the problem completely right now. So T of 9. So I hope everyone is able to follow. So T of 9 will be something like this, 4 plus 8 plus 16 plus 22 plus 63 plus 125. So it will be 12, 16, 28. So it will be 48, 56, 60, 123, and then 125. So it will be something like 248. And then T of 10. T of 10 will be the sum of these values. So it will be for 56 and okay, now it's getting a bit messy. So what will this value be? Maybe I can use a calculator on my side. Although this shouldn't require a calculator, but yeah. 248 plus 125 plus this will be 95, and then this will be 101, 111, and this will be 119, right? 60, 90, 100, and 190. So this will come out to be something like a 492. If you guys want to verify, you can do these calculations by yourselves also, as I'm doing right now, like along with me. So so this will also help in verifying these solutions. So T of 11 will be again a sum of values till this. So this will be 492 plus 248 plus 125 plus 63 plus 32 plus 16. This comes out to be something like 976, I believe. And then T of 12 comes out to be 492. So T of 12 will be sum from here to here. So it will be 492 plus 248 plus 125 plus 63 plus something like a 1936, I believe. Okay, so Rasika is also saying in the chat that T of 12 is 1936, and yeah. So I believe this should be the right answer. So thanks, Rasika. So yeah. So the since T of 12 is 1936, so the number of ways to construct sum 12 by throwing a dice one or more times is something like 1936. And you can see that why I'm saying that replacing this dice one or more times by zero or more times won't matter is because a sum of 12 can't be anyways constructed if I throw a dice 0 times, right? So the only answer which will change if I throw a dice 0 or more times or one or more times will be this answer, that T of 0. And if I throw it 0 or more times, then this makes my life easier. So that's why I'm doing this sense. So I hope you guys get this. So this is the answer, and so I have underlined the answer also. So then I guess if this is clear, we can move on to the next question. So maybe I should put put this on the next page. So this would be similar to a question. So yeah. So consider the following 5 items with their weights and values. So we are given 5 items and we are given their weights and the values of those items. So like item 1 has weight 7, value 28, item 2 has weight 11, value 55, and so on. And our task is to pick a subset of these items such that their total weight should be lesser or equal to 13. So we can only carry a weight of capacity 13, and the total value which we obtain should be maximized. And we can either pick an item fully or we don't pick the item. So I hope you guys understand what the problem is asking. So what the problem says is, just to reiterate that we need to pick out of these 5 items, some items such that the weight of those items, the given weight of those items should be less than equal to 13. But the value which we obtain from those items should be maximized. So suppose we are a thief or let's say someone who needs to carry some stuff, and we need to maximize the total value which you obtain out of that stuff. But the capacity of our carriage is only, let's say, 13 kg, and we can't carry more than 13 kg. So we need to find out the maximum value which we can pick, the, the maximum weight which we can pick for these items. So one thing to note here is I would like to point out that someone may directly think that the best way to move forward may be to pick the items in the value by weight ratio, that pick the item which has the highest value by weight ratio, because then the item, this sort of implies that the item will have a more value for lesser weight. So one may think that way. And this sort of thing I also covered in my greedy lecture, but this sort of thing does not work for this problem. And why does it not work? So actually, so if we can see all these items by their value by weight ratio, then this item number 1 will have a value by weight ratio of 4. Item 2 will have a value by weight ratio of 5. This will have 17. This will have 8, and this will have a 7. So what we would pick is this item number 2, item number 3 first. So because this has the highest value by weight ratio of 17. So if we pick this item, then this has a weight of 2. So we are only left with a weight of 11 now. And we can fill up this weight 11 using the remaining 4 items. And the highest value by weight ratio out of these 4 items was of this item, the item number 4, which has a value by weight ratio of 8. So if we pick this 2 kg, then next time we'll pick this 4 kg. And if we pick this 4 kg, our weight will be 6 kg. And now we can only pick a weight less than equal to 7 kg. So the only remaining eligible weight will be this weight of 7 kg. So if I follow a very greedy procedure of picking the items with the highest value by weight ratio, I'll obtain the combination of item number 1, item number 3, and item number 4. So I'm just doing all of this orally because. So yeah, Harsha is right in the chat that this is a knapsack problem, and what I'm discussing is greedy. So I'm just showing Harsha that in knapsack the greedy algorithm does not work. So first of all, I'm just describing this orally because I sort of described this in one of the previous lectures also, in the greedy lectures. But just reiterating this fact that why do we need, so one needs to understand why we need a better approach than greedy, right? So for that, I'm presenting just a counterexample. Okay, so where was I? So I was just saying that if we pick item number 1, 3, and 4, then we'll have a weight of 13 kg, and we would have maximized the possible value, and we would have picked these items using the value by weight ratio rule. Like take the maximum value by weight ratio item first, then the second, then the third, and so on till you can pick. So this gives us a value of 34 plus 32 plus 28, which will be something like a 66 plus 28, which will be a 94. So we can obtain a value of 94 if we pick the items by this greedy rule of value by weight, where we pick the items 1, 3, and 4. But what I claim is we can have a different set of items uh, using which I can have a value of more than 94. So what I'm showing is this greedy approach will not be correct. So the 94 kg, so we can beat this 94 by picking the items. Which items should we pick for beating 94? So you can just directly see, like, uh, if I pick this item number 3 and item number 5 only, if I pick item number 3 and item number 5, what happens is the weight is still less than 13 kg. So these two are feasible items, and their weight and their value already is 97. So item number 3 and item number 5 together beat the greedy rule of item numbers 1, 3, and 4. So 1, 3, and 4 together had a value of 94, whereas these 3 and 5 together will have a value of 97. So at least we see that there exists uh, some set of items like which are better than the greedies, which are better than picking just the greedy set. Okay, so Harsha is asking in the chat that if instead of a sequence, it were a matching, do you think greedy might work like stable marriage? Uh, so I'm not sure if I understand your question here, Harsha. So what do you mean by this is a sequence and it were a matching instead? Like, what's the sequence here? Knapsack is a sequence depending on many levels. So I'm not sure if I'm able to understand your problem correctly. Like, are you talking about the problem itself, Harsha, or are you talking about the DP algorithm which we'll be using for knapsack? Uh, if you change the problem given here, instead of knapsack, you were to give a problem of matching kind. Uh, I'm not sure if I understand this correctly, but just pointing one thing out, Harsha, in your question that in matching also, greedy is not optimal. Like in for finding matchings in a bipartite graph, let's say, greed is not optimal. Greed is not an optimal algorithm for finding a matching in a graph. So I don't know if this statement answers your problem or not, but so yeah, stable marriage. So stable marriage is a greedy algorithm, but what I'm saying is a bipartite matching. Okay, so you're saying that BPM BPM is bipartite matching, right? And stable marriage you're saying is so. I'm not talking about stable match right now. I'm just talking about bipartite matching. Like if we want to find the maximum bipartite matching, then greedy does not work. Yeah, stable matching involves greedy, but you can see like there is just not a greedy idea in stable marriage also, right? There are some things like first you propose to the person who is your favorite, but then maybe the person also rejects and in next step you propose another person. So like greedy is not a fixed technique for every problem, right? Greedy just describes that like you choose what is best at any step, but there can be some changes while keeping the algorithm. Like the essence of the algorithm is definitely greedy, but what algorithm you are describing also matters. Like if one just says that a greedy algorithm for stable matching problem, like this will also be a greedy algorithm, right? That just try to match every partner with their most preferred choice, but that won't be stable. Oh yeah, so you're saying something like there's only one level of greedy. If it were to be replaced n minus one times, it becomes BPM. Harshash, would you like to? So should I enable your access to the mic? Would you like to ask this problem in on the mic, because I'm not sure if I understand this while you're typing. Okay, so I think you can unmute yourself now. Harsha, maybe you can unmute yourself now.
No, sorry, please go ahead. Actually, like I just wanted to know actually, like if we were to change the nature of the problem, uh, then I think maybe sometimes maybe 3D might have worked as was for. I just wanted. I was curious to know what your thoughts. So just spitballing actually on the scenarios, actually, like how if we had redesigned this problem, actually maybe. Uh, if it were one level, maybe greedy sometimes works actually like much more faster. And if there are more inputs, then sometimes it is preferred actually. And that works only if it is one level. If it is a sequence, for sure it doesn't. So, but even in one level, actually, if you need an optimized way, actually, then yeah, PPM is one way. Or maybe if there is cost involved, then you can use MCMF. Thank you.
So I don't know much about like I don't know much about like the levels of greedy or stuff like that. So I'm not sure if I'm the right person to ask this out to. But just going a bit off on a tangent, like if you're just asking about finding a maximum bipartite matching, let's say, then greedy is not optimal for that. And yeah, so I don't know if this helps you or not, but using greedy in bipartite matching, I know this for a fact.
No,
Other
no,
than
that is
that,
true. What you said is true. I was just changing the scenario. But what you said is the that's how it works. But what I was saying is no issues. Please go ahead.
maybe we can move on to further discussion for the problem itself, like solving the knapsack problem. Like maybe this is a maybe I guess we are going on a tangent. So yeah, sure. Thanks, Arsha. So Rasika was also, I believe, asking something in the chat. So uh, you're typing something in the chat, right, Rasika? Maybe you can ask it. Okay, it's clear. Nice. Okay. So I guess we can move on to this fifth question. So yeah. So was just describing that so I was just describing that greedy is not optimal. Uh, greedy is not optimal for this sort of problem. This is called a knapsack problem actually. That where we are given a weight capacity and we have to find out the maximum value constrained by the weight. So this is called an abstract problem, and uh, this the greedy does not work in this problem. But actually, you guys can see for yourself, it's more of a fun fact that even though greedy does not work, it does not do too bad either. Like we can always prove that like there's a proof which says that greedy this sort of greedy algorithm which I just described, the solution picked by greedy algorithm will be at worst twice worse off than the optimal solution. So let's say the optimal value which we can obtain is something like 100, then greedy will obtain at least half of it. Like if we use greedy algorithm, then we'll obtain at least 50. Or if let's say here the optimal solution is something like 200, then if you use the greedy algorithm, then you will always obtain at least 100, and so on. So greedy is not too bad either, but it's not optimal. And we are right now like the problem we are right now interested in optimal. The the fact like the fact it's just a fun fact which I was stating that greedy always picks a half, but you can ignore that also if you want. So yeah. So here okay, so we first of all, so now we know that greedy does not work. So maybe we'll have to use dynamic programming. So maybe you guys would have seen this problem is called the knapsack problem, and maybe you guys have seen this knapsack problem earlier. So so maybe if we want to find out dynamic programming using dynamic programming, would one of you like to point out like what sort of dynamic program should we use, or what sort of recursion should we define to solve this problem? Okay, so yeah, so Rasika is saying bottom up approach. So I don't know exactly what stage based is Harsha, but I believe so. Yeah. So I was just asking you guys like here we define something like a t of n as the minimum cost to reach the nth zone. So what sort of thing can we define here? So actually, what we sort of define here is something like a 2D array, which is like a 2D variable tij, which essentially states that okay, maybe I should like this, since this is not an array but like just a variable. So tij, and what this actually states is that uh, so maybe before going on to this, maybe you can just see in the problem statement itself. So suppose suppose in our solution, in our final solution, we pick the item number 5. Suppose we pick the item number 5, although we have suppose in the final, so there are two choices that we either pick the item number 5 or we don't pick the item number 5, right? So if we pick the item number 5, then we know that initial highest capacity which we could carry was 13. But since item number 5 has a weight of 9, so now the capacity reduces from this 5. Like, so if we pick the item number 5, then the capacity reduces to 4. So now what we want to do is from items 1 to 4, we want to maximize uh, the items picked with a maximum capacity of 4. And if we initially did not pick item number 5, then what happens is from items 1 to 4, again, we just want the maximum, we just want to pick the maximum value items and have a limit and have a capacity of 13 on the items. So what I'm trying to say here is that TIJ denote the So what TIJ essentially here denotes is the maximum total value uh, obtained if we pick items from 1 to I. From the set 1, 2, 3 till I. So what we do is we don't pick out of all, so these are just 5 items. So let's say we are given some n items. So we don't pick out of all those n items. We just pick out of the first I items. Maybe I should write it. From the first I items. Okay. If we pick a subset from the first I items with total weight less than equal to j. So what are these I and j variables? So what I'm doing is, suppose I consider only the first I items. I pick out of those I items, and I have a constraint of the total weight being maximum j. So this is what I'm trying to say. And how did this idea come up in my mind? Like, why can I pick, like, why do I make this sort of setting that I pick from only from the first I items and I pick from a maximum of total weight j? So this idea came up in my mind from this only. Like, suppose I took the last item number 5, and so there were two cases. What I could have done is I could have actually picked my item number 5 in the final solution. In that case, what I had to do was, from the items 1 to 4, I had to pick items with maximum capacity of 4, because 13 minus 9 will be 4. So I need to have sort of a variable already stored which stores the total weight less than equal to 4 from the first 4 items. And similarly, if I did not pick this item number 5, then again I can only pick from the first 4 items. But this time I have a maximum weight capacity of 13. So that's why I need something like this. So I hope this is clear to you guys. And what will sorry for that. So what will be the recursive relation here? So T of ij will be nothing but, so there can be two cases, right? Maybe I should just write down the maximum of two cases. So case one is item I is picked, and second case is item I is not picked. And how can we write the value in these two cases? So I could have directly written the recursive relation also, but I just want to everyone to understand, like, how do these recursive relations come about. So that's why I'm writing this step by step. So there can be two cases, that either we pick item I or we don't pick item I. So if we actually have picked item I, then what happens is I have obtained a value of vi. So I'll assume that the value of an item is given by this number vi. So if I pick the item I, then I have obtained a value of vi already. But what I need to do is now, like, I have also expended some of the weight, right? The weight remaining. So what I need to do is, I can only collect a weight of now j minus. So the maximum weight which I was allowed to carry was j from the first I items. So if I have picked the item I, then the maximum weight which I am allowed to carry now becomes j minus the weight of I, because I have already picked the I item, so the remaining weight becomes lesser. And now I also need, and I can only pick from the first I minus 1 items now, because I've already picked the item I, and this will become something like a j minus weight of item I. So I hope this expression is clear to everyone. If this is not, maybe you can ask in chat. I'll try to explain this again. So this is the value obtained if item 1 is picked. And similarly, if item 1 is not picked, then we don't get this vi because we don't get any value. But what we get is now from the, what we need to do is from the first I minus 1 items, we need to pick max of, like, pick till j. Pick items with a constraint of j. So for finding t of ij, what I actually need is t of I minus 1 comma j minus wi and t of I minus 1 comma j. So these two values I should compute first, and afterwards uh, I would be able to uh, obtain the value of Tij also. So I hope this relation is clear to everyone. If it is not, you can let me know via chat and I'll try to explain this again. And what will be our final answer? The final answer will be nothing but so final answer is nothing but T of. So what we want is out of first, we want to pick out of first 5 items with a weight of 30. So something like this is what we need to find out. And how do we go about calculating this? So for finding this out, we need to find out like T of 4 comma something and stuff like that. So yeah. So now the next thing which is important is to see how do we actually, in what order should we calculate these values? Like for Tij, for computing Tij, we need to have computed first this Ti minus 1 comma j minus wi. So we know something like this, that for computing an entry of Tij, we should have computed all the entries of T of I minus 1. Like T of I minus 1 comma j for all j should have been first computed if we want to compute any entry of T of I comma j. So we'll be going sort of row by row, like if the row represents the items and the columns represent the constraint on the weight, then we'll be going something like row by row. So we'll be filling row 1 first, then we'll be filling row 2, then we'll be filling row 3, and so on. And in this manner, actually, we can find. So maybe, so what I'm trying to say, is it clear to everyone? Uh, Now we need to, in what order should we uh, calculate the values of Tij? And the idea is if we consider this as a matrix with Tij denoting the entry at ith row and jth column. So this will be a cell at ith row and jth column. Then we first compute entries of the first row, then the second row, and so on. So what we actually need to do is we need to compute the entries of the first row. Then from the first row, we can compute the entries of the second row. And from that, we can compute the entries on the third row and so on. And for computing the entries on the first row or something, uh, so maybe I can show this also. So maybe we can insert a table. So, so yeah, let's consider this table. where like let's say again this the column represents the first column represents like this column represents weight equals 1, this weight equals 2, weight equals 3, weight equals 4, weight equals 5, and so on. And these all are the ith entries like I equal 1, I equal 2, I equal 3, I equal 4, and I equal 5. Right. So what we can actually do is so we need to compute this sort of value that this will be something like a t of 1 comma 1, which will say that the maximum total value obtained if we pick a subset from the first item with total weight less than equal to 1. So this entry will be sort of 0 because we need at least a weight of 7 for the first item. So so maybe I'll have to do a lot of computation here, like in the lecture itself, because we'll need something like a 13 columns because the maximum capacity is 13. But do you guys sort of get the idea of how do we fill up the table? So first I need to fill up this whole row. Like I need to fill up this entry, then this entry, then this entry, then this entry, then this entry, till so on. And then I will fill up this entry, this entry, this entry, this entry, this entry. And after computing these two rows, I'll compute this, and so on. So the order of computing the entries will be something like a T11, then T12, because first row, second column, T13, and so on till T113. And then we'll move on to T21, T22, and similarly again we'll move on till T230. And this will again repeat in the third row, like we'll move on to third row also. And this will keep on till we find out the value of T of 5, 13. So note that even though this looks like a lot of steps, like these are not a lot of steps if you code it in a laptop, because like if you run it in a program, like it will compute it quite efficiently. But this is sort of the idea for finding out the for solving this knapsack problem. I hope everyone is able to understand this. If it is not, maybe you can ask in chat and I'll try to explain it a bit better. So let's for now keep it at this only. Let's keep it at this theory that we need to use this recursive relation and then compute these values to get the final answer. And maybe I'll just post the final answer also when I'll upload this document. So I'm not computing it right now, but because I don't remember the answer correctly, but while uploading this document, I'll just update that what is the final answer here. So you can do this, you can try this yourself also, finding out the final answer. So yeah. So if this is clear, if the idea for this problem is clear, maybe we can move on to the next question, which is the sixth question. So, okay. So sixth question defines a problem, subsets a problem, subset some problem, and we are also given the code for that. So it's a bit relaxed question. So the subset sum problem is defined as follows. So given a list L of n non-negative integers and a value k, determine if there is a subset of elements from the list L whose sum is equal to k. So what we are given is we are given a non-negative integer in a subset sum problem, and we are given a value k. And we have to determine if there is a set of numbers from the list whose sum is exactly k. So we are just given a number k, and we have to find out from a given array if there exists some number whose sum is actually exactly equal to that number. And actually, the subset sum problem also we have to use something like a DP, and the DP code has also been already given to us. So consider the following solution code where T is a 2D Boolean array. So we are defined a T array which has n plus 1 rows and k plus 1 columns. So something like Ti, and that entry Tij actually denotes that if there is a subset from A1 to AI, so again A1, A2, A3 till AN are the entries of the list. So maybe these should be small subscript. So yeah. So what Tij denotes is like this is very similar to what we defined in this knapsack problem. So here Tij denotes that if there is a subset from the first I elements whose sum is exactly equal to j. So like in knapsack problem, we said that Tij denotes if there is a subset of first I elements, like we have to find the maximum of the first I elements whose values is less than equal to j. Similarly, here we find out if there is a subset from first I elements whose sum is exactly equal to j. So this is what Tij holds. So now I think you can by yourself also describe what the relation for Tij should be, but luckily we are also given this index code also. So we are given this T array which we have already initialized, and now the main relation for Tij has already been given to us. So what happens is so for I, so this is just the base case that for I in range n plus 1, Ti0 is true. So what this means is that so Ti0 means that if there's a subset out of first I elements whose sum is 0. So this is true because if you don't choose any element, then the sum is always 0, right? So that's why Ti0 is true. And now we run a loop for all I and for all j for filling up these values of Tij. And how do we do it is that so mm, so there can be two cases, right? The ith element, the AI element can be actually greater than j. And if the AI element is greater than j, then AI element will never be included, right? Then AI element like there are two choices. Either we can include this element AI or we can exclude this element AI. So if we include the element AI, then if AI is already greater than j, then the sum cannot be equal to j anyways, because all the numbers are non-negative and we have already obtained a number which is greater than j. So that's why in this setting, we just set its value equal to if L of I minus 1, this is just the value AI. If this is greater than j, then we just set Tij equal to T of I minus 1j. Because if AI is greater than j, then we can't include AI anyways. So the problem just reduces to finding out of A1, A2 till AI minus 1 whose sum is equal to j. So this problem reduces to I minus 1th part. Or second case can be like or the other thing can be like so this is the main crux of the problem then, that there are two choices for us, that we can include AI or we can exclude AI. So if we include AI, what happens is now we have to find out from the first I minus 1 elements whether there exists an element, whether there exists a subset of the sum j minus AI, because we have already included AI. So this is the part which gives us the value that for the first I minus 1 elements, uh, does there exist a subset of the sum of which has sum exactly equal to j minus of AI. So L of I minus 1 actually denotes AI value only. The second case can be if AI AI is not included in in our final answer. And if AI is not included, then it's just equal to T of I minus 1j, because the problem reduces to finding out a subset from first I minus 1 elements. So this is what Tij will be actually equal to, because Tij is what gives us like whether from the first I elements there exists some whose sum is exactly equal to j, something like that. Okay, so I hope this is sort of clear to everyone. Then in the given code, so the option, the question, so this is the idea behind solving the subset sum problem. So like we have already written the code, and yeah. So now the problem just asks us like what should we return in the answer? Like we have briefly discussed how to solve the subset sum problem. So what should be the value which should be returned by our function? Like what value do we actually want? Which entry of the array T should be returned? Which, if true, implies that there is a subset of elements whose sum is exactly equal to. This is a very straightforward question. Would any of you like to answer this? So the options are T1k, Tnk, Tk1, and T0k. So note that what did Tij represent? It's true if and only if there is a subset out of A1 to AI whose sum is exactly equal to J. And we need to find out from this array N if there exists something like. Come on, guys, like this is a question like which you guys should be able to answer if you have been following this. Like, you don't even need to go through this code, I believe. Like I was just describing this code to give you an idea of like how do we solve this subset sum problem. But you just need this statement to find out like which value should be finally be returning. Okay, so Harsha is typing something. Okay, so this is the question, Harsha. So the sixth question is what I'm discussing. This question, in the given code, which entry of T should be returned? If true, it implies that there is a subset of elements whose sum is exactly equal to k. And this was what the Tij was defined. Like Tij is true if and only if there is a subset of A1 to AI whose sum is exactly equal to j. Okay, maybe I can revise of this. So what we actually want in the problem is there a subset of elements from A1 to AN whose sum is exactly equal to k? So I will be nothing but equal to n and j will be equal to k. So it is something like a T of n comma k, which is the option B. Uh, it won't be T of 0 comma k actually, Asha, because T of I denotes like T of 0 will denote nothing. Like T of I denotes if there is a subset from A1 to AI whose sum is exactly equal to k. Maybe while Asha types in chat, B. I'll write this down. Since we need to find out if there is a subset of elements from A1 to AN whose sum is equal to K, Hence, I is we should return T of nk. So yeah. So this running this. So hence option B is correct. Okay, so you can define the problem in that way also, Asha, but the problem, the solution which has been defined in this manner that Tij is true if and only if there is a subset from like you can define this problem in this manner and then solve it accordingly. Like if one has defined it in some other manner, then they can solve it in other manners. Okay, sure. So you understand now. That's good. So the answer will be something like a T of nk, which is option B here. Then next option is okay. The next option is the next question is again just related to this question 6 or only like it's just asking us what is the time complexity of this function which we have implemented it. So what would be the time complexity according to you guys? So the options are n square, n log n, n plus k, and nk. So this is another problem which I believe we should be able to answer. Okay. So Rasika is saying that answer should be order nk. So yeah, that's good, Rasika. That's the correct answer. And why is this true? Because we are just running two loops which go from 1 to n and 1 to k. And in each loop, we are just doing constant amount of work. Like either this statement is getting executed or this statement. So it's just order nk. So option D is right. Option D is correct. And this is because we have nested loops with outer loop of n iterations and inner loop of k iterations with constant amount of work done in each iteration. So this is the outer loop with n iterations, inner loop with k iterations, and constant amount of work in each iteration. So yeah, this is a straightforward question. And then, so this is the last question for the day now. So this is the eighth question. So the number n is to be, so the eighth question says that, let's say the number n is to be created by adding the elements. Uh, so what the problem actually says is that we want to create a number n by adding any elements of an array, and one element can be used more than one time. So an element can be used multiple times from a given list of m positive integers. So we are given an array of length m, and from this array of length m, we can add an element more than once also, and we wish to create a number n from this. Like, can a number n be obtained by adding some elements by using an element more than once also from an array of length m? So let's say one tries to write a code for this, and the person actually does not use uh, so this will be the sort of code which a person will have to use. So so the answer will be something like this, that if n is 0, so if number n is to be created, and let's say the number is 0, which we want to create, then it can be created by just an empty list, right? Because no numbers means that sum of numbers is 0. Again, and similarly, if n is less than 0, since every element is positive, uh, we won't be able to create. So answer will be none. So, and now the main part of the answer comes. Now, what does this part do? Uh, so we have this array of length L, right? So what we can actually do is an array L, which we have of length M. So what we can do is, let's say we take the first number of that array and we use that number to make the sum. So what happens is, let's say we take the number I from this array L. So what we can do is we try to solve the problem now that suppose we have used this number I, then now we just need to make a sum of n minus I now, because initially we wanted to create a sum of n, but since we have used the number I, we just want to create the sum n minus I now. And note that since one element can be used more than one at a time also, so this I element can also be reused. So all elements of this array L can be reused. So that's why the second part will still be L. That So essentially the problem says that you check this number I and check if using this number I, we can, like, after using this number I, can we make sum of n minus I using all the array elements. So we do this and we find out, like, X returns the list. X actually returns the list of numbers which will be used to give this sum of n minus I. And if actually this is possible, that we are able to obtain the sum of n minus I, then this means that the actual answer is nothing but we can create this n minus I using this X and then append this I. And this will give us the answer to n. So if this is possible, then we obtain a list of numbers whose sum is exactly equal to n. And if this is not possible for any element, like if we try for every element and we obtain that this is not possible, then we'll have to return none, that it is not possible. So I hope this loop is actually clear. Like, I don't think this recursive relation is too difficult to see. So we just check for every element if ith element will be used or will not be used, or something like that. So the problem asks us what will be the asymptotic complexity of the above recursive function without and with memoization. So suppose to implement this, what we can do is we can write it like this only, and then this n sum function will be called again and again and again and again. So it can be called something like an exponential number of times. And maybe we can save this calling exponential number of times using memoization. So any idea, guys? Like, what if you just use recursion and don't use memoization, what will be the complexity? And if you actually use memoization, what will be the complexity? Okay, so Harsha is saying that the answer should be 1. The option A should be the answer, that the time complexity using recursion without using memoization will be m to the n. And if we use memoization, then it will come down to mn. Okay, so uh, are you sure? Do we need order mn in memoization? Like, what I'm saying is, see, initially we are solving something like n sum of n comma l, and while calling some sub problem, again we are using something like n minus I comma l only. So do we really need to store this l also? So this is the problem, Harsha. So even if you don't know the problem description from this code also, it can be seen, but yeah, maybe you can see the problem here. I think there's an issue in options also. So option should be like this, and then this would be correct. Like, or maybe like we can keep it as this. But do you see, Harsha, what I'm trying to say? Like, using memoization, we don't need this order mn space. We just need something like an order n space because this L does not reduce anyways in our code. Cool. So you see this. So yeah. So order mn won't be needed. Only order n space would be needed. I believe there's some mistake in options. My bad. And if you use recursion, then I believe it's straightforward to see the time complexity. So Rasika is saying that if we use recursion, the complexity will be something like 2 to the n. So I don't think that's quite correct, Rasika. I don't think. Yes, Harsha, L is input array static. So Rasika, 2 to the n won't be needed. I think there will be more. So yeah, so Harsha is correct that Harsha is saying that each time we are calling this function, we are running a loop. We are running a for loop which runs m times. And note that since we need to make the sum equal sum of n, so this for loop can so this will sort of create a recursive tree where uh, there will be m children for every node, and the depth of this tree will be something like n. So this will actually be something like an m to the n, not 2 to the n, because at each time of calling this function, we are running this loop m times. And if we are running this loop m times, and this function can be together called like something like an n times, because we need to create a number n. The answer will be something like m to the n. Maybe I should yeah. So yeah. So if we put these two like m to the n, m to the n, then the answer will be something like an option C here. Like m to the n is required while recursion, and without recursion we only need order n. So I hope you guys see why this is true. Option C is correct. And why is it the case? Maybe I will just write down a few words. Uh, this is because at each, this is because if we don't use memoization, so maybe like, okay, suppose another thing to note is that like, okay, I don't think there's anything to note, but I'm saying that order n is correct. But maybe if someone implements it using order mn, it will not be efficient, but it will still be correct, right? So if suppose there was no option which had order n in these options in the exam. So I'm just talking in terms of exam, not in terms of like knowledge or anything. In exam, if there was something like an mn but no order n in the options, then maybe you can choose the order mn one. But strictly speaking, for this problem, it requires only order n memoization. This is because if we don't use memoization at each call of the function, the for loop runs m times, and so m copies of the function are called. Since we need a sum of n, uh, there can be the depth of the recursion tree can go to n, with each node having m children. So what this means is that so without memorization, it will take order m to the n time, or maybe it can take order m to the n time. And with memorization, we just need to store the values of n sum I comma l over all I, and note that L does not change in the call, in the recursive call. So only order n. Okay. Okay. I believe I sort of I also sort of got confused. Okay. So the problem asks just the time complexity of the above recursive function, right? Okay, so I believe the answer will be order mn only for the memorization. So we'll only require order n space. That is correct, Harsha. But what the prob what but while solving this problem, what we have to do is for computing every value of the table, like for computing, let's say ith value of the table, or let's say the nth value of the table, we'll have to run this for loop m times, right? Like we'll have to go through this for loop. So we'll have to go through m values. Like for computing nth value, we'll have to go from like for all I in L. So we'll have to iterate over m previous values for computing one value of this memorization table. So that's why so for computing each value will take order m time, while there will only be n values. So time complexity will be order mn. Space complexity will be order n, but time complexity will be order mn. So yeah, I mixed data, but yeah, option A is actually correct. So only order n space is required to memorize, but computing each of these entries will take order m time. So overall algorithm takes order mn time with memorization. Okay. So hmm, so yeah. So I guess this is it from my side. So this was the last question which I want to discuss. So Rasika, I just want to ask, do you understand why 2 to the power n is not correct? Like why it will be order m to the n and not 2 to the n? I can maybe explain it again if. Okay, you got it. Nice. Okay, so I guess guys, so this is all what I wanted to discuss for today. So I'll upload this video also and upload the document also on the Google Drive link, and I'll update the final answers with the final values for these answers so that you can check these yourself also whether what you have computed is correct or incorrect. So yeah. So other than that, I guess since we are out of time. Okay, so Rasika is saying that video lectures for week 11 are not uploaded. Okay, so maybe I'm not so sure, Rasika, but I believe that there will only be problems for week 11 and 12, because week 11 and 12 problems will be based on dynamic programming, and lectures for dynamic programming have already been done in week 10. So from now for the next 2 weeks, no lectures will be uploaded, only problems will be uploaded. So we'll be discussing in the next 2 sessions also some more advanced problems may be related to dynamic programming. So these were some standard problems which we discussed today. So we'll be discussing some more and trickier problems in the upcoming weeks. So yeah. So other than that, since we are running out of time, so I believe we are already over time. So I guess we should close this session. If there is any small doubt, maybe you can ask in chat. Other than that, otherwise we can just close the session now. Okay, since no one is typing in chat, I'll assume that no one has any doubts. So I guess I'll just stop sharing and you can leave the session, guys. Thanks for joining. Hopefully, we'll see you guys next week also. Same time, Tuesday 6 to 8. Okay, thanks for coming, guys. Bye bye.